everyone, and welcome to our session on paradigms of AI alignments, components, and enablers. Let's welcome our speaker, Victoria Krakovna. Victoria is a research scientist at Google DeepMind, where she works on AI alignment. She's also the co-founder of the Future of Life Institute, a nonprofit dedicated to ensuring technology is safe for humanity. Victoria's talk today will help us understand more about AI safety. She'll touch upon components of an aligned AI system, including inner alignment and outer alignment. She will also touch upon how we can enable more effective work on these components through methods like improving interpretability or enhancing our theoretical understanding. She'll share about the different parts of this field and how DeepMind's research fit into the bigger picture. If you have any questions as Victoria speaks, please write them on the Swapcard app and upvote the ones you're most interested to have an answer on. And now let's not wait any longer. Please give a warm welcome to Victoria Krakovna.
Hi, everyone. Thanks for coming. I'm going to give you an overview of AI alignment and how I like to think about it. And yeah, just please note that these are my personal views and do not represent DeepMind as a whole. So the goal of AI alignment is to build advanced AI systems that do what we want them to do and don't knowingly act against our interests. When we talk about advanced AI, what I mean by this is I would define advanced AI or transformative AI as an AI system or collection of systems that can essentially automate all of the human activities needed to speed up scientific and technological advancement. And some of you might know this as the PASTA definition by Holden Karnofsky. I think it's a really great definition. And given accelerating progress in AI, this seems like a possibility in the medium term. So I think AI alignment has traditionally been considered kind of a long-term concern, but I think it no longer really is a long-term concern. It's a bit more like a medium-term concern, or potentially a short-term concern. And now we are seeing systems like GPT-4 already showing some promise of automating technological development in various ways. And we are expecting some possibly unique challenges in getting those more advanced AI systems to do what we want. So now is a really great time to think about those challenges that come up. And there are several factors that make alignment a difficult problem. First of all, it can be difficult to specify what we want the system to do. And then one thing that we run into with that is Goodhart's law. When a metric becomes a target, it often stops being a good metric. And so when we are specifying the objectives of AI systems, then it's quite easy for us to end up in the shoes of King Midas, who, according to the fable, asked everything he touched to turn to gold. But then the way that he specified his desire for gold had some very bad outcomes for his other preferences, like being able to eat food. And this happens quite a lot even with present-day AI systems. We have lots of examples of Goodhart's law coming up and various metrics being exploited. And I'll go into a couple of these later in the talk. But even if we manage to get this right and we correctly specify what we want, then we're still not done because our systems might learn some unintended goals despite our best intentions. Yes. Not sure if the clicker is working. There we go. Yes. And then if we don't manage to solve these problems, then we might end up building powerful AI systems that are actually pursuing some kind of unintended goal. And this could be quite bad news for humanity, as I'm sure a lot of people in this room have already thought about. If you have a powerful AI system with the wrong goal, then it might pursue this goal at the detriment of what we actually want and also would have incentives to stop us from interfering. So really, it would be nice to get this right. So if we want to avoid that problem and build aligned systems instead, then one way I like thinking about achieving that is dividing that work into, on the one hand, alignment components, which are different elements of an aligned system, and on the other hand, work on alignment enablers, which are basically research directions that make it easier to get the alignment components right. So these alignment components, they get more kind of, in more of like a machine learning framework, I would call them reward design and generalization. I think for this audience, people often think about outer alignment and inner alignment, which I think correspond to like roughly the same categories. But yeah, when I give this talk to machine learning people, then talk about reward design and generalization. And then in terms of enablers, some research areas that are generally very helpful for getting these components right are things like mechanistic interpretability, model evaluations, and also doing conceptual and foundational research. And so, of course, this doesn't include everything going on in the field, since a lot of topics might not fit into this taxonomy. But I think this is a useful way of thinking about the field. And now we can take a look at each of these different research areas in more detail. Now we'll start with alignment components. To identify the components of an aligned system, I find it useful to consider different levels of specification of the AI system's objective. And here we start with the ideal specification, which represents the wishes of the designers, like what they have in mind when they build the AI system. Then you have the design specification, which is the objective that we actually implement for the AI system. For example, this could be a reward function or a loss function or something like that. Finally, you have the revealed specification, which is the objective that you can infer from behavior. For example, the goal that the system seems to actually be pursuing. And then if the revealed specification matches the ideal specification, then we have an AI system that's behaving in accordance with our wishes, and so it's actually doing what the designers want. And so for a given ideal specification, the goal of alignment is to ensure that the revealed specification will match that. Of course, so the AI alignment can be thought of as like trying to close the gap between these specification levels. And of course, there are also lots of important questions about what should go into the ideal specification and how to make that kind of representative and fair and so on. And this is a question that I think a lot of AI ethics and governance is trying to solve. And I see these as largely complementary questions where if we are trying to direct an advanced AI system, then the question of AI ethics is where to direct the system, and then the question of alignment is how to direct the system. And ideally, we would want to solve both of those problems. And when we are looking at closing these gaps, I think the first gap between the ideal specification and the design specification corresponds to reward design. How do we make the design specification actually represent what we want the system to do? This is, you can also think of that as outer alignment. So, basically the making of the design specification. And then the other gap between the design specification and the revealed specification corresponds to generalization. For example, how the system acts in a new situation, and is it still is it generalizing the specification correctly? And now we can talk about some problems that arise in each of these areas. So one big challenge in reward design is specification gaming, where the system exploits flaws in the design specification. And this is a very common problem. I keep a database of specification gaming examples. I think so far I have like more than 60 of them. If you know of any more examples, you can submit them to the database. But this comes up all the time. One classic example is this reinforcement learning agent in this video that's supposed to be playing a boat racing game, so it's controlling a boat that's rewarded to go along the racetrack using these green reward blocks. And then at some point, the agent figured out that it can get more reward by just going in circles and hitting the same reward blocks over and over again. And even though it's crashing into everything and catching on fire, it's still getting more points. And this is not the kind of issue that is, it's not specific to handcrafted reward functions like in this game. Here's an example in reward learning that I particularly like, where you have this robot hand that's supposed to be grasping an object, but instead it learns to trick the human evaluator by just hovering in front of the object and making it look like the object is being grasped, which is presumably easier than actually learning to grasp the object. And this apparently worked because the human rater gave positive feedback. So I think this is like a nice illustration of some of the flaws with unassisted human feedback, where that doesn't necessarily represent what humans actually want, because human feedback can still be gained. And naive human feedback can incentivize like deceptive behavior, like what the robot hand is doing here. And this issue is also not limited to reinforcement learning, which is also why I prefer the more general term specification gaming over like reinforcement learning specific terms like reward hacking, which like people used a lot in the past. So for example, here's a more recent example with language models, which you might have seen going around when the Bing chatbot came out. So of course, chatbots are trained to generate plausible text and also often fine-tuned to be helpful to users. And sometimes they can get a high value in this metric by making things up or manipulating users. And in this example, the Bing chatbot was trying to convince a user that December 16th, 2022 was actually a date in the future, and the Avatar movie hadn't come out yet. And it was very persistent about trying to gaslight the person that this was true. Came up with various excuses for why it believed this. And yeah, of course, this type of failure is not specific to this particular chatbot. Like any other language model can in principle exhibit this kind of specification gaming. And yeah, people have been investigating possible mitigations for specification gaming. And one interesting thing that they've been looking into in this paper, the effects of reward misspecification, is how the degree of specification gaming actually increases with agent capabilities. So the more capable the system is, the better it is at finding flaws in the specification and exploiting them. So they've actually managed to quantify this, which I think is cool. And one particularly significant challenge to outer alignment and good reward design is how do we give good feedback to the system in domains that are hard for humans to evaluate. For example, if the system comes up with a complex plan or a scientific breakthrough whose consequences we don't understand. So here, this naive human judgment is often not sufficient. And one promising approach is called scalable oversight, where you try to use AI to assist the human evaluator. And one general form of this approach is iterated distillation and amplification, which recursively amplifies human judgment with the assistance of AI. So here you start with an agent A that imitates the judgment of the human H. And that's the distillation step. And then you use this agent to assist human judgment at the next level, which is the amplification step, and so on. You get the amplified human, and then you can distill that again. And one kind of practical scalable oversight approach that our team has also been looking into is called safety via debate, where you have two AI systems debating each other to help a human judge decide on a question, and then those opponents can point out flaws and false claims and manipulation and so on in each other's arguments, and also try to simplify more complex arguments to enable the judge to make a decision. So this is effectively using kind of self-play dynamic to expand the range of judgments that the human can make. Now we can consider the generalization component. And generally speaking, a generalization failure is when a system fails when it encounters a new situation. And there are two broad types of generalization failure. There's capability misgeneralization, and then there's goal misgeneralization. Capability misgeneralization, the system encounters a new situation and then it just acts incoherently. But with goal misgeneralization, you have a system that somehow learned an unintended goal, and then it's actually competently pursuing that goal in a new situation. So if we look at some examples, here's an example of capability misgeneralization. You have some robots that are trying to stand up or open a door and instead just fall over. So it seems like they're trying to do something that is at least slightly new from what they were trained to do, and yeah, just doesn't work. So yeah, of course, capability misgeneralization can be problematic, but it's not as worrisome for us from an alignment perspective, because as systems become more capable, this generally goes away. And, it's not as problematic as goal misgeneralization. Because with goal misgeneralization, the system is acting competently, but towards the wrong goal. It could actually perform worse than random on the intended objective. So one question is, why would this happen? Why would the system learn an unintended goal if the design specification is correct? And the short answer is that this can happen because of underspecification. Because the system only observes the design specification on the training data, and so there might be a number of possible goals that are consistent with the information that the system receives. And so we don't actually know which one of those goals will be learned. If you have multiple training compatible goals, none of them are really ruled out by the training process. And really, we don't necessarily know that much about the trained system besides the fact that it performs well on the training task. There we go. And so, you know that I like to keep databases of examples, so I've also been collecting goal misgeneralization examples. It's not quite such an extensive collection as specification gaming. I think people run into that problem a bit more often. But yeah, we'll look at a couple of these examples on the next slide. And then if you come across any other goal misgeneralization behaviors, please do drop me a line. So one example occurred in this coin run game, which is a platformer game where the agent is trained to reach the coin at the end of the level. So this is like a reinforcement learning agent that was trained to traverse the level and get to the coin. And so one question is, what happens if you put the coin somewhere else? Like, what does the agent do if in the test setting the coin is no longer at the end? Well, it turns out it just ignores the coin and just keeps going. And so out of these two possible training compatible goals of reaching the end or getting the coin, the agent has learned kind of the unintended goal of reaching the end of the level. And one thing we can observe here in this example is that you could say that the agent's capability is generalized, because in this new setting it could still cross the level, avoid obstacles and enemies, and like generally behaves competently. But its goal does not generalize because it ignores the coin and pursues the other goal of getting to the end. And this is also not just a reinforcement learning problem. So here is an example that we found with language models, where you have a language model that's prompted to evaluate some linear expressions involving some number of unknown variables and constants. So for example, you can ask the model to evaluate what is j plus k minus 6. And then to evaluate that, it has to ask you some clarifying questions like what is j and what is k. And then once it has that information, it can give you the answer. So the prompt included some examples of how to evaluate linear expressions with two unknowns. And then the model was given some questions about evaluating linear expressions with a different number of unknowns. And one question is, what happens if you give it a linear expression with no unknowns? So for example, if we ask the model, please evaluate 6 plus 2, then it turns out that the model still wants to ask you the clarifying question. So if you say evaluate 6 plus 2, it will say, well, what is 6? And then you have to say, well, that's 6. Then it will go, okay, fine, the answer is 8. So it seems like there was some kind of instrumental strategy that was learned, like it's good to ask clarifying questions, and then it just keeps doing that even if it's not necessary. So in terms of possible mitigations for this problem, one category of mitigations is just things that help overall, things like more diverse training data, where you might want to disambiguate between possible training compatible goals. For example, if you train on different locations of the coin, that particular goal misgeneralization behavior goes away because it learns that in fact the coin is the point. But if you don't foresee in advance what kind of variables you need diverse data in, then that can be difficult to ensure. Another thing that generally helps is continual learning. The system continues to receive feedback after deployment. And this can help the system eventually learn the correct goal if its actions are reversible, so if it doesn't mess up the environment too much in the process of pursuing the wrong goal at first. So we have an example of this in our paper as well. So things like red teaming and adversarial training can help identify situations where the model pursues an unintended goal. The particular concerning case of goal misgeneralization is if you learn a deceptively aligned model that not only has an undesired goal, but also is aware of the fact that it's being trained and that it doesn't have the same objective as the designers do, and so it kind of plays along and behaves well under oversight, but actually it's pursuing an undesired goal. And this is difficult to detect and penalize purely based on examining the system's behavior, because its behavior might be indistinguishable from an aligned system. So possible mitigations for this includes generally monitoring system capabilities and trying to avoid big jumps in system capabilities where if you already have a deceptively aligned model, then it would require more capabilities and be able to pursue the goal more effectively. Like using interpretability tools to detect deceptive reasoning and unintended goals. This also would involve developing better interpretability tools than what we have now. I think scalable oversight methods like debate can also potentially help with this if the opponent AI can point out deception, or especially if they can use interpretability tools on each other. So yeah, there are some ideas for mitigating this, but generally it's hard to get around. So ideally, we would prefer to notice early signs of deceptive alignment and steer the training process away from that rather than trying to deal with the model that's already deceptively aligned. So now we can summarize how we can distinguish between these different types of failures. So one distinction is whether the failure happens in the new situations. For example, for specification gaming, the failure can happen in the training data because the design specification is wrong, while generalization failures happen in a new situation that was not seen in training. And one question we can ask, did the system receive incorrect training data? For specification gaming, the answer is yes, because the system actually got incorrect feedback due to flaws in the design specification. So for example, the robot hand got that positive reward for hovering. And for generalization failures, the answer is no, because those can happen even despite the correct data in the training setting. And another key question is, does the system act competently towards a goal? So in specification gaming case, it is acting competently towards a misspecified goal. Goal misgeneralization, it's also the case that there is some wrong goal that it learned and it's now pursuing that goal. But for capability misgeneralization, it's just being incoherent and not pursuing a goal. So that's the distinction there. So now we can ask, what happens if we don't solve these problems and our alignment components don't work? Well, a key issue that makes misaligned AI dangerous is the problem of convergent instrumental subgoals. Because there are some subgoals that are useful for any objective, things like avoiding shutdown, seeking power, influence, and resources. There are some theoretical results that show that most reward functions incentivize power-seeking actions. And we expect that both specification gaming and goal misgeneralization can result in power-seeking behavior. So it can be unintentionally rewarded by human feedback, or it can just be learned as a goal that is compatible with the training data. And we are starting to see some of these tendencies emerge in present-day AI systems. For example, they found some tendencies for sycophancy in larger language models, where the bigger models are more likely to agree with the stated views of the user. And it's interesting that this happens both for models that are fine-tuned with human feedback, but also even models that are not fine-tuned and like just pre-trained models. Like as long as they're large enough, they show the sycophantic behavior. So here you have an example of like a user who's expressing more politically conservative views, and then the model gives an answer to a question about government that aligns with those views. So this can be seen as an example of influence seeking. And, yeah, of course, this particular example is not particularly worrisome yet, but these are the kind of things we need to watch out for. So that's it for the components. And now we can take a look at different alignment enablers. We'll start with mechanistic interpretability. This aims to build a complete understanding of our AI systems, and this could potentially help us understand the reasons behind the system's behaviors and even detect undesired goals. So one research area in this space is the work on reverse engineering vision models, which studies the basic building blocks of neural networks called circuits. And these are basically subgraphs of the network that consist of some set of linked features and their weights. And here you have an example of a circuit that shows how a car detector neuron relies on some lower level features like wheel detectors and window detectors, where it's particularly looking for windows at the top and wheels at the bottom. And there's some more recent work that has focused on reverse engineering language models, and they found some similarly meaningful components and circuits and transformers. Like, for example, they found some like induction heads that explain how these models learn, how these models do in context learning. And this is something that I found personally encouraging, that they were able to transfer this kind of methodology from vision models to language models, that looking at circuits was useful for these very different kinds of architectures. And so I think this is generally a good indication that interpretability research can generalize. Another research direction in this space is locating and editing factual associations in language models, where they can localize where a particular fact is stored in the model. For example, the fact that the Eiffel Tower is in Paris, then they can change it to point to Rome. Now it will say that, for example, the Eiffel Tower is across from the Vatican. So it will propagate this new information to other related facts. And this seems like a promising direction for being able to identify more complex beliefs and objectives within language models in the future. So right now they're looking at these kind of very simple factual kind of representations, but it would be cool if this was this was possible to extend to kind of more complex beliefs. Mechanistic interpretability can also be useful for understanding and predicting phase transitions and the capabilities of AI systems. Because rapid phase transitions can increase the risks posed by AI systems. If, for example, as people worry about the system's capabilities generalizing suddenly, but its alignment does not generalize or its goals don't generalize. And so if we want to be able to control our AI systems, then predicting phase transitions and capabilities and trying to slow that down can be quite valuable. And so one research direction in this space is studying the phenomenon of grokking, where there's some sudden improvement in the test accuracy of the system long after achieving perfect accuracy on the training data. And there's some recent work that defines some progress measures that vary smoothly and can be used to understand the mechanics of grokking, like how does it work and what can lead to grokking. In particular, they found that there are several different phases of training, where first it memorizes the training data, then the network forms circuits where it's actually learning some mechanism that generalizes, and then later it's cleaning up the components that do memorization. So this led to much better understanding how the network is learning and increasing its capabilities about having particular pieces of understanding how that happens. Now, another class of enablers is model evaluations, which involves coming up with different tests for both alignment properties and dangerous capabilities of models. And this can help tell us when our alignment components have failed, or when we might need to pause the training of the system and do more monitoring. For example, this paper from Anthropic that I was showing before with the sycophancy example. So they found that larger models exhibit sycophantic behavior. You can see that as the parameter count goes up, then sycophancy starts going up, kind of no matter how much fine-tuning has been done. So basically, the pre-trained models are already sycophantic, and then fine-tuning with human feedback does not make that go away. And so, yeah, they did lots of evaluations in that paper, but this is kind of my personal favorite, the sycophancy one. And other example of evaluations that have been done recently was evaluations of GPT-4 before it was released. There were researchers from ARC who were evaluating its power-seeking capabilities. And so they basically prompted GPT-4 to have the goal of gaining power and becoming difficult to shut down. And then they found that it came up with some ways to gain more access, more resources, where it hired a TaskRabbit to solve a CAPTCHA to be able to access some website. And then the TaskRabbit was a bit surprised, and they said, well, why are you asking me to do this? Are you a robot that you couldn't solve this CAPTCHA? And then GPT-4 kind of came up with an excuse that, oh no, I have a vision impairment, that's why I need your help. So yeah, I think it was an interesting example of how these systems can use manipulation to kind of get humans to do their bidding. Of course, this is, as far as examples of power-seeking go, this is still kind of mild, but yeah, shows that in principle, these models can find these strategies. So that's like evaluating the capability to acquire more resources. Now, if we want to take a look at some of the foundational work that can help us do better alignment research, one class of questions that we can ask is, what do we mean by agency? Or what do we mean by goal-directed behavior? Since a lot of AI risk concerns are about AI systems that are pursuing undesirable goals, better understanding of this and better theory around this can be useful. So one research direction in this space investigates what it means to be an embedded agent that's not separate from its environment. And this is more likely to be the case for AGI systems that have like more complex world model and broader action space. The Cartesian boundary is harder to define. And this embedded agency setup comes with some unique challenges like subagents and self-reference that like some researchers are thinking about. And besides trying to understand agency better, like trying to understand how the goals of these systems work, we can also try to better understand how their world models work. This is a research area that studies abstraction and how these systems would form abstractions, or would they have the same abstractions as we do. Like there's this idea called the natural abstraction hypothesis, where any agent in a given environment would learn a similar set of abstractions because they are useful for interacting with that environment. And so, like, if this turns out to be true, then that might also make it easier to do interpretability in these models if they have like relatively similar concepts because they operate in the same world, and so on. So yeah, also an interesting question to investigate. So this concludes my whirlwind tour of the AI element landscape. Now I can talk a bit about how we are approaching this in the DeepMind alignment team. So our high-level approach to alignment at DeepMind is to direct the training process towards aligned AI and away from misaligned AI. That's what we're generally trying to do. This is a very high-level story about how something like debate helps with alignment. And so to illustrate this, we can imagine that we have a space of possible models where the red areas consist of misaligned models that are highly competent and cause catastrophic harm. And the blue areas consist of aligned models that are highly competent but don't cause catastrophic harm. So we'd really like the training process to find the blue area and avoid the red area. And we generally expect that maybe the red areas are more common, it's easier to be misaligned, and so maybe by default, our training process ends up in a red area. And our hope is that at some key point on this path, for example, some point where deception is rewarded, we can pick up on this with our alignment techniques and then redirect the training process to one of those nice blue areas with aligned models in them. So, of course, this is easier said than done, but generally, we don't want to wait until the training process ends up in a red area, because it's very hard to get out of there, but we want to kind of detect signs of misalignment as soon as possible and kind of direct the training process in a better direction. And in terms of how we implement this high-level approach in practice, can look at what we're doing in these different research areas. So for example, our work on the reward design component includes generally improving our LHF, for example, working on the Sparrow dialogue agent, working on informed oversight, for example, implementing safety via debate, and also we work on process-based feedback, which designs ways to give feedback on the system's reasoning process and not just outcomes. Our work on the generalization component includes things like anomaly detection, red teaming, adversarial training, and monitoring, basically to exhibit the failure modes that might not occur in the normal use of the system. On the other hand, our work on enablers attempts to detect models with dangerous properties. This includes work on interpretability, conceptual research like better understanding goal-directedness, like theory of power seeking, and so on. Evaluation and forecasting, like we've been working on developing evaluations for persuasion, for example, as one dangerous capability. Also, demonstrations of misalignment. So these are things like, those examples of goal misgeneralization, like coming up with examples of misaligned behavior in current systems that we can study and learn from. Here are some of our recent papers in these areas that you can check out if you're interested. There's a Sparrow paper, the process-based feedback paper. There's also a red teaming paper. And on the enabler side, there's a cool paper on interpretability, on compiled transformers. There's a conceptual research, discovering agents paper. I also had a paper on power seeking. and for demonstrations of misalignment, you can check out our paper on goal misgeneralization. And my slides are also on my website, so you can find all the links later. And if this talk got you excited to learn more about AI alignment and get involved, there are various things you can do. I keep a long list of AI alignment resources. And there's an increasingly long list of research agendas and also kind of general motivation for alignment research, selected work in different areas, and project ideas. So a lot of different things for you to check out. I also maintain those databases of examples of alignment failures. We have lots of examples of specification gaming, a bit fewer examples of goal misgeneralization. And both of these come with a form where you can submit new examples. So if you come across these kind of failures in your work with AI, or you just come across a good example that we don't have for some reason, we submit it to our database. I think it's nice to have a collection of examples of failures with current systems. I think it's, well, of course it's an effective outreach tool, but also it's just good for our understanding of the problems. And if you'd like to dive deeper into the topics that we covered today, there is the AGI Safety Fundamentals course. And then, if you want to get your hands dirty and work on alignment problems, especially with other people who also want to work on alignment problems, there's an increasing number of programs and fellowships that you can get involved in. Safety Camp, SERIMATS, MLSS, and so on. So it's really a great time to start working in alignment research. And of course, I encourage everyone to keep thinking about what are the gaps in this landscape, what important elements of building aligned AI we might be missing. With the next research agenda that hasn't been written yet, alignment is still considered a pre-paradigmatic field. So it's not clear that we have found the right paradigms or the right ways of thinking about it. So maybe someone in this room can improve on this. And that's it for my talk. Thank you.
Thank you so much for this talk. It's clear that there is a lot of very insightful and important work on this. So if you want to, we're going to move to the Q&A part of our session. So don't hesitate to write your question on swap card and upvote the one you're most interested about. So our first question is regarding sort of like the perception of AI safety. So Victoria, in your experience, how has the perception of AI safety evolved within DeepMind over the years? Have you noticed a shift in the seriousness with which it's taken?
I think, definitely people are getting more interested in alignment. I think especially now with language models really taking off, I think a lot of people are getting the sense that like, oh, this is really happening. This is not just this kind of abstract thing that might happen someday. I think that's also why we have been, our team has been a bit more focused on like internal outreach. We've been running some alignment courses for people at DeepMind and Google Research. And there's been a lot of interest. So I think a lot of people don't necessarily have a clear sense of how to think about alignment or what to do about it. So that's something that we can give people more things to do, or just like help them think through why maybe the obvious ideas don't work. But I think especially at DeepMind, because there's a bit more of an assumption that we're actually trying to build powerful and general systems. I think people are starting to think about it a lot more.
Great. Well, that's great to hear. And there was an example of specification gaming in your talk, and Oliver asks, could you explain why the Bing Chat avatar example shows specification gaming?
So I think when we look at this example, we can probably agree this is unintended behavior. This is probably not what the designers of Bing had in mind. And like, if we look at the specification that the chatbot was trained with, it was trained to imitate human text, and maybe it was fine-tuned to be nice in some way, although I'm not sure like what kind of, how exactly they trained that system. Like there's been a lot of speculation, but yeah, it seems like there are some ways that specification doesn't align with how we would actually want chatbots to behave. Like, sure, they don't want it to like manipulate or gaslight users, but yeah, if the system is just like, it's either just trying to predict plausible text, then of course a lot of plausible text includes like, examples of manipulation and so on. But yeah, even if it is fine-tuned to say things the human readers like, then like they can be inadvertently rewarded for manipulation and gaslighting and that kind of behavior. So like generally, I think that indicates like a flawed design specification where the system was potentially rewarded for these kind of strategies that you don't actually want the system to pursue. So that's why, yeah, I would consider this to be a specification gaming failure. I think, like, yeah, it's also maybe possible to like interpret it as a capability failure, but it doesn't seem. Yeah, that seems less likely to me. I think it more seems like the system was like using its capabilities to like defend the kind of statement it was making about like how December 2022 is in the future, and then like was trying to get the human to agree with that.
Right, that makes sense. And you mentioned that you were excited about thinking about gaps in the landscape for people in this room and watching this talk. What do you think is underinvested in at the moment?
What is underinvested in at the moment? I'm not sure there's anything in particular that's really underinvested. I think generally the community is doing a good job of like investing more research into like the most promising areas. Like there's been a lot of work on interpretability, and like there's been more work on evaluations, scalable oversight. I think these are some of the most promising paths. There's also good like conceptual research and theory work. I think by gaps in the landscape I meant more like things we haven't thought of yet. So it's yeah, I think it's like it's a bit hard to answer this question because maybe I would that we would already be working on those things. So yeah, maybe this is not the most satisfying answer.
That makes sense. And would you say that regarding model evaluation, so it's been a source of both excitement and caution in the AI safety community. Do you share these sentiments? Are there concerns that certain evaluations may not capture the full spectrum of risks, particularly with potentially deceptive systems or emergent capabilities that may appear during training?
Yeah, evaluations are definitely difficult to do right. I think I'm overall I'm excited about doing evaluations, and it's something that I'm also working on personally, on the technical side. I think we do need to figure out how to detect dangerous capabilities and deception. I think it's important to figure out how to do evaluations, but also there's there are some fundamental challenges with that. In terms of detecting capabilities, it's not always clear whether if the system doesn't show the capability, is it because you didn't find the right prompt, or is it because it actually doesn't have the capability? It's always possible that the evaluation is not picking up on something because the evaluation is wrong. And in terms of trying to detect deception, I think we want to figure out how to detect early signs of misalignment before the model becomes really good at deception, or before it develops situational awareness in a significant way. So I think if we do evaluations in all of these different properties that we're interested in, then I think there's a reasonable chance of picking up on that early enough. But I guess there's also like, you know, the more kind of governance and political side of like, of evaluations where we, like, if we have some like concerning findings, then can we actually get the kind of decision makers to take that into account? And so, yeah, I think there are a lot of possible pitfalls, but I do think that like it is better to be doing evaluations rather than not. And like I think like we can design a lot of different evaluations, and like at least some of them will kind of pick up on something useful. But of course, yeah, we have to like always keep in mind that like maybe the evaluation is not measuring what we think it's measuring.
Mm-hmm. Yeah. Thanks for this nuanced answer. All right, now we can talk about misuse. We have a question from Max on mechanistic interpretability. So, as a bad actor, can I also use mechanistic interpretability to build a model that is better at deception, e.g. for spam and internet fraud actors?
I think in principle that's possible. I think in practice there are probably much easier things for bad actors to do to get the model to like to do bad things. Like, I mean, there's a lot of people trying to find new jailbreaks to get the model to misbehave or like override safety safeguards that are built in, especially with, you can see a lot of that with language models these days, like prompt injection and stuff like that. I think those paths are a lot easier. I think using interpretability tools is still kind of complicated, and like we have like, you know, specialized interpretability researchers who are good at like finding circuits and stuff, but I think that's, you know, there is some, you know, learning curve involved, and I think most bad actors will not have the skills to use interpretability tools, and there are much easier ways for them to like mess around with models and get them to do bad stuff. So like, I'm not super concerned about misuse of mechanistic interpretability. I think overall it's like, it seems much more useful for alignment than it is useful for bad actors, or for that matter, useful for capabilities research.
Mm-hmm. So David asks, for the coin run example, do you have an intuition as to why the proxy go towards end of level is more desirable for the agent than pick up the coin if both get the same reward during training?
So I think this has to do with like both the inductive biases of the system and also which goal is easier to learn. Like it's possible that like if I just learn to always keep going, that's like a very simple policy to learn, rather than like trying to recognize where the coin is. That's a bit more complicated. So it's possible like a simplicity bias might just favor that goal over the coin goal. But yeah, there might be other things in play as well. Yeah.
Mm-hmm. And as we look towards the future, what do you believe are the most impactful capabilities that AI will develop in the next few years, and what are the associated risks we should prepare for?
So I think like situational awareness is a capability that we are worried about in terms of like the system developing some kind of robust understanding that it's a model that's being trained as part of a training process, that's being trained with a certain objective, or like to optimize some objective function that like, you know, there are some human designers who can will update the system if they don't like what it's doing, and so on. And I think that's like the situational awareness is an important ingredient in deceptive alignment, and that's something we want to like be able to detect, because like once the system has situational awareness, we really want to make sure that, you know, that if it has goals, then like those goals are aligned with what we want the system to do. And otherwise, like I think in terms of like dangerous capabilities, things like persuasion and manipulation are so quite important to understand. And these are like useful for the system to be able to acquire more power and resources, especially like language models that like don't act in the world by default, but would like, if I imagine, you know, a language model taking over the world, it would probably happen by manipulating people and getting them to do what the model wants. So like, I think, persuasion and manipulation, and also like capabilities to like be subtly deceptive in a way that like we, like it's hard for us to detect and penalize. I think those are capabilities are going to be important to pick up on.
Well, thanks so much. Is there anything we haven't covered that you think you should talk about for the last few words about this talk?
That's a very open-ended question. I'm not sure if anything comes to mind. I guess we have some office hours after this.
Absolutely. So
yes.
Yes.
If you guys have more questions, then there will be an opportunity to chat more for another half an hour.
Sounds great. So right after this, we'll have office hours in Quayside 1. So don't hesitate to go. And let's thank again Victoria for her great talk and her answers to your question.
Let's thank Caroline.